Hello everybody, my name is El Barbero and today I like to talk about fatigue, specifically specimen fatigue. This is video number 3 in this series. Video number 3 we're going to see how to get all the parameters for the specimen, and then on video number 4 we'll do the same for the component. All right. And I'm going to show you how to get the parameters from data and how to get the parameters from estimates. There are very few things that can be estimated, and then we have to figure out how to get all the parameters, and that's all the complexity. So if you want to complain about the equations, that there are many equations and the equations are difficult and they're hard to remember, then you have to understand that if you didn't have this equation, then you cannot estimate anything and you're forced to get data. And to get data costs money and time. By the time they do all the experiments and they charge you, you're going to regret it and you're going to say, oh, I wish I knew this equation, I could estimate. All right, so that's my justification for this. Okay, so bear with me. All right, so then we move on. But first, a little bit of review from a past video. You remember sometimes I say component and sometimes I say part. I mean the same thing. And I need to mention the component or the part to differentiate from the specimen, because like I said many times, the specimen is a standardized. It's small and of a fixed size, is polished, is subject to bending only, tested at room temperature, and so on. So it's very clear what we're testing. Component is more broad. It could be large, could be different loads, different surface, different temperature. And on next video, number 4, we're gonna learn how to deal with that, okay? Everything for a specimen will be denoted with a prime, like here, like any SC prime. I didn't put the prime before, and sometimes I don't put the prime on the drawings, because why make 2 drawings if all the equations are basically the same? You just have to remember that if it's a specimen, then you put the prime. So these equations down here are for, right now in this presentation, are for a specimen. Okay, so then that means that there should be a prime there and a prime there. It's not that I forgot. But why bother? I don't want to remember 2 equations. Just remember 1 equation, and if it's a specimen, we call it prime. And in here, okay, the only thing we put the prime is on the C, because it's a parameter. SUT is the same for a specimen and component, because SUT is the tensile strength of the material, doesn't care if it's a specimen, component, what. And it's quasi-static, so it doesn't even belong into fatigue. And fatigue strength, we always call it SF no matter what, because that's the value of stress at which the specimen or part will fail. Okay, so we call it SF, all right? And so then you say, oh, but he forgot the primes here. Where I forgot the primes? It's not that I forgot, it's I don't forget, it's I don't want to do 2 drawings. So we put the prime like this, and this SE is for specimen. It was determined with the R.R. Moore specimen, so we put a prime there. And we're pretty much done. Here we have a variable with prime already that we know is for specimen. This one doesn't have anything. Then we got this, we got the F. No, but the F doesn't have a prime because F and F prime are the same. And the reason for that is that in this region, from here to here, for the low cycle fatigue life, all the factors that make a part or a component different from a specimen, let's say, is larger, okay, or the surface is not polished, okay, do not have a bearing on this region at the beginning. When these locations are coalesce and they are getting together before they make a crack, they don't care whether it's a specimen of a part and what the size is and stuff like that. Only when we go into this region, yes, then it matters if it's a specimen or not. That's why the F is independent. It's just the same. So we keep it like this, all right? And it's defined like this, all right? So that means SF measured at NT, which is this number, will be 100, and divided by SUT, SUT 125, so 100 divided by 125, F is 0.8, okay? in this case. If we had the data, super easy, 0.8, done. All right, and then in the previous video, we derived an equation for the LCF slope, low cycle fatigue slope, which is this, which would be C prime. Well, but C and C prime are the same. And so log F, which are the same, prime or not, divided by log NT, and it gives you the value of C, and we can move forward, okay? All right, so then with that review, we can keep on going. Okay, so now what I did here is I start with the data, and I put if you have data, which you should have. Because like I said before, the best is to have data. Maybe you can get the data from the supplier of the material. Usually the suppliers do this. They do testing and they have data. If you ask, they will give it to you. Because having data, you know what you're working with. It's not just assumptions like we will do later. And I call them homework assumptions or preliminary design assumptions. Things that I assume, but I'm not sure about. For me, the best is to have data. So if you have data, it's very easy. You just put it in Excel and then you get all the parameters, like I'm showing you here. So what I did is I went in here in this diagram, all right, and I digitized the plot. I digitized the plot and I put the data into Excel, okay? And when I put the data into Excel, I discovered that yes, I can put the real data n instead of log n and tell Excel, please give me log scale here, fine. Then I can put the real SF, fatigue strength, with no log in another column, and then that's for this axis, and then tell Excel, please put it in log, yes, and it will do it, yes. But then when I try to do the linear regression, I mean the easy way because I'm lazy, basically I right click on the data and I say regress the data. It didn't do it because it doesn't do linear regression with two log axes. At least I couldn't make it work. So then I decided, oh, okay, I'll do it the hard way. That is, you take the n data, you take the log in another column of Excel, and then you plot that normal in a regular scale. You see, 2, 4, 6, 8. Now, what does 2, 4, 6, 8 mean? Well, 0 means 1, 10 to the 0. So that means in log is 1. In the previous it says 10 to the 0, right? And in this one, it just says 0. What about 2? 2 is 100. 4, 10,000. 6, a million. Okay, you get it? All right, so then in this axis, okay, before in the other plot, we had, 50, 100. Where's the 50, 100? It's gone. So now I got this 1.7, but if you do 10 to the 1.7, that's 50. So this will be the 50, okay, which happens to be this value here. We can label it as E prime because this is for a specimen. But it's not 1.7, it's 50 because you have to take 10 to the 1.7 to get that 50. And so on and so forth. Like for example, the SUT was 125. Well, we more or less guesstimate that is 125 right there. Yes, 100, 10, 20, looks like 25, okay? We'll see in a minute that exactly is not 125, but okay. So what's the 125? Well, you take 10 to the 2.1, and then it's going to give you 125, okay? So this is SUT, okay? All right, so once I do that, then I click on the blue dots, and I say, please give me a linear regression, and please put the equation on the graph. And so here's the equation, but these numbers are all in log, okay? Because this is in log, so these numbers are in log. And then regress this one, and there I got it like this. And then I put a horizontal line more or less like that by eyesight at 50, which here it says 1.7, but now you know what it means. And basically we get everything, okay? So what do we need? We need SUT, all right? Yes, SUT is there, 10 to the 2.1. We need C prime, which is equal to C because in low cycle fatigue, which is this region, C and C prime are the same. So where is this? Is the slope of this curve, so is this number here. Yes, with a minus, you see, it's going down. Okay, so from that you can get C. And we need the sigma F prime. Okay, where is sigma F prime? Sigma F prime is the intercept of the high cycle fatigue. High cycle fatigue is there, right? So we gotta intercept that. So let's see, I don't have a ruler, but I have a piece of paper. And you don't see it, but I'm putting a piece of paper on this. And then I'm extending this line. Okay, there we go. That looks better. Okay, and somehow this is going away. Okay, so when I extend this line, and then I have an intersection, and here I have sigma f prime. All right, but sigma f prime 2.2, no, 10 to the 2.2. It's something like 160, I think. Okay, let me say, calculator, shift 10 to the x, 2.2 what? 2.2 or 56, because this is the intercept. It's right there, yes? Or 56. And that's 160, okay? 160. So this is 160.5, yes? And one thing I have to say is when you do calculation with logs, please carry several, at least 4 digits. Here there are 5 digits, 2, 2, 0, 5, 6. So because 10 to the x, if you make a little bit of a rounding and you put 2.2, you're not going to get 160, you're going to get 155, something like that. So the errors accumulate very fast with logs and with powers. And this is a problem when you do homework, because web work has tolerance, but not that much, all right? And so for the homework, you have to be accurate, all right, to get the system to accept your answer. All right, so so then we have C, we have sigma prime. We need B prime, that's the slope of the high cycle fatigue life. And SC prime, what about SC prime? Oh, SC prime is there, you know? And so, what is this? Like we got the 1.7, 10 to the 1.7, it will give us 50. So if we got the data, it's piece of cake. You transform the data to log both axes. Yes, use linear regression. Then you get these equations. From the equations, you know everything. The intercept, this intercept, by the way, 0.0913, yes, you take 10 to this value, it should be SUT. And SUT, which we are by eyesight, we say is 125. Maybe we do it exactly, it's not going to be exactly that. NT and NE we get by eyesight. So basically, wherever these two lines intersect, I think they intersect a little bit farther than 100. This will be 100. I think they intersect more like in 200, which will be there. Yes. And then NE, well, NE is clear, is right there. Yes, this is 10 to the 6. Okay. And then what about F for that we need here? You know, for this point we need F SUT. Okay, well, it's easy. We get NT to the C. Once we decide what we want to put for NT, let's say 200, the power C, which we already calculated, and then give us F, and done. It's super easy, okay? So in the next slide, I will show you the results, all right? And so this is what I was talking about in the previous slide, but now it's summarized. From the plot, here are the parameters. Did I label them correct? Yes. Okay, the values which I calculated in the Excel file directly are these, and how I calculated 10 to the 20913. So this 20913, you do 10 to that, they give you 123, no 125. Okay. SC prime, is where this line is, which is 10 to the 1.7. 1.7 is here. You do that, and they give you 50. C, is the minus 0.0326 from the trend line equation. B prime, minus 0.0831 from the trend line equation. And then NT is visual, 10 to the 2, well, maybe it's 200 instead of 100. And then your choice, here it's hard to say. Then 10 to the 6 is right here. Then sigma prime is this, 2056, which is this. 10 to that, they give you 160, which is right here. And then, so sigma prime will be here. And so, and then F, we can do this calculation and you get 0.86. 0.86 is reasonable because I know the F's could be, you know, 0.8, 0.9, maybe a little bit lower than 0.8. But usually they are between 0.8 and 0.9. So this is reasonable, okay? So from Excel, it's very easy, very, very easy, okay? Okay, I stopped the recording just a sec to verify that I had the numbers right on the screen, because these two numbers here, I thought, oh, okay, do I get the correct numbers? Let's see, do I get the correct numbers? And so I come here, and so I thought, yeah, but they are the correct numbers. See, what I can do is I can calculate C, which here I'm just calculating from the trend line. So this is C. Yes, and the slope, this, well, C prime, well, it's the same. And this is B prime. Yes, directly. And I thought, oh man, I don't have to put the log or the 10 to the x on those. And how do I know? I go back and I have this, my trusted equation that I derived last video. C is log F, yes, divided by log NT. NT is 100. Okay, I pick 100. And F, I just calculated it's 0.86, but I got it. And so I'm convinced, and this is negative, yes. And the B prime, is the B prime right? It must be right because it's also negative and it's larger. This is 0.3 and this is 0.8. Yeah, it's going faster. So, okay, I'm satisfied. So we can keep on going. All right. So now, okay, so now what happens if we have no data? All right, so, okay, no data. To do homework, we have no data, so we got to do something. So if we have no data, then we have to play with the equations, all right? So we take the HCF lines, high cycle fatigue, we go in this region, and then we say, okay, our equation is SF, if I put a prime there, sigma F prime, yes, this is the intercept, times n to the B prime, yes, this is B prime, okay? You want the prime, we can put the prime there. Okay, so at n equal to NE, which will be here, SC prime, like that, has to be sigma F prime multiplied by NE to the exponent B prime. Because that's the equation, and this equation is valid for all this region from here to here, all right? So when I evaluate it here, this number has to be equal to this, okay? Now multiply both sides by NE to the minus B prime, okay? And then divide by SE prime, and so I multiply by this, I get NE to the minus B prime. That kind of kills this. And then I have sigma F prime, and I take the SC prime down, and I got this equation, yes? Now, when I have this equation, take the log. When I take the log, then what happened? The minus B prime go down here, log NE equal to log of this, yes? And so log of all these, right? Like if I do log of this. And so, okay, so now from here I can get B prime, okay, minus log of sigma F prime divided by SC prime, divided log of NE. And here now you have an equation that is super important, because if you have no data, how are you going to get the B prime? You cannot do the regression like I did with Excel because you have no data. So you say, okay, I can do this equation. And if this is like the old-fashioned, we assume that this is true, then you can simplify a little bit the equation, but not much, because, okay, minus, this is the same. And log of NE, well, if NE is 10 to the 6, obviously, that's a 6, so here's the 6, yes? That's a 6. So, okay, you have this equation. So how am I going to calculate B prime? Well, the thing is that these two numbers can be estimated for carbon steel. Yes, low carbon steel. There is a lot of data. I'll show you. And so if you can estimate these two numbers, then boom, you have the B prime. All right. Okay. So then, right, we have the B prime. What else? Again, I don't have no data. So no data. There's no B prime. We have the equation that we like and we remember. And here is to emphasize, sigma prime is the ordinate at the origin of the linear regression of the data. So it's here. And SC prime is the entrance limit from data, okay? But we don't have data, right? Okay, and NE is the entrance life also from data, but we can assume it's 10 to the 6. It's right there. So what are we going to do? This is what we're going to do. If data is not available, here no data, not available. All right, then we can use this estimate, but I cannot guarantee that this estimate will work for modern materials because this is for carbon steel, alloy steels, and rough iron from a very old time, from the 1950s. Okay, I didn't track down exactly this graph, but most of these graphs in the textbook were created in mid 20th century. So you work with modern materials, you're gonna have to get your own data. Okay, even if you're working with these materials, this estimate, I don't know, I have no idea how accurate it is, but this estimate, SE prime, is here on this plot. You see here, this is entrance limit SE prime, there is S, very tiny, SE prime, and tensile strength SUT, all right? And they say, okay, estimate with this equation. SE prime is 1/2 of SUT. Oh, how nice equation, very simple. You know the SUT, everybody knows the SUT. Take half of it. But is that really reliable? Well, I mean, it could be 0.5, which is this line. We kind of goes through the middle of all the data, so yeah, okay. But if you look at the other data, you draw this line, and that's 0.6, and that's 20%. And then if you go down here, that's 0.4. All right, that's 20% the other direction. So there is a plus minus 20% error there on that coefficient alone, okay? The rule also says that if the SUT is kind of high, which would be for modern materials, if it's high, then I'm afraid to take half, and I'm just going to take, it doesn't matter if SUT is 210 or 300 or 350, no, I'm going to take 100. So I'm just going to cap it to that. And that is for conservative reasons, but who knows if this applies to a modern material. And this equation here is in megapascal, so it's the same equation, but translated to SI units. And okay, so, but for homework, oh yeah, we're gonna use this because we have no data, so these equations for us are what we're gonna use, okay? So then again, why we need these estimations? To calculate the B prime with this formula, okay? We have this formula, all right? So then we go to the next, and then since we have the B prime, now let's go after the F. Like I mentioned before, F and F prime are the same because during low cycle fatigue, component and specimens behave the same, okay? Approximately the same. Now, from the definition of F, you remember, which is the same as F prime, is the value at NT, that is this strength, which in this case is 100, divided SUT, which is 123, and that's going to give you F, okay? But that is if you have data, yes? So if you have no data, then you gotta have another equation that allow you to get this number, because I cannot do 100 divided 123 because remember, now I don't have data, all right? So what I do, I say use the HCF line, high cycle fatigue line, which is this line, that says SF and NT, how much is the value here? This value is sigma F prime, and where do I get this? I got it from here. Yes, and so, and then NT, well, NT I can assume, all right, because I don't have data, so I have no clue. Yes, if you have no data, you have no clue. So people will assume is this, 10 to the 3. And B prime, where do you get B prime? Oh, we just calculated B prime. Okay, so that's it. I can calculate this value. If I can calculate this value, since this value everybody knows, and this value I can calculate, this is my formula for F. And so you put this formula aside and you keep it handy because it's the one that lets you calculate F. And once you have F, you can calculate other things. Of course, for the particular case, NT 10 to the 3, if that's what you're going to assume, the formula simplifies, but not much because, okay, the 3 goes there, but no big deal because NT is 10 to the 3, is 10 to the 3 to the B prime, okay, power on it's multiplication, so that's it. All right, so it's the same. Okay, so we have we have F. Okay, now let's do a summary. Again, we have no data. Let's do a summary. Equation for low cycle fatigue, SF prime SUT n to the C prime, no, prime is the same. High cycle fatigue, SF is the intercept, which is this here, which we can calculate or estimate. How? Here, with this equation right here, bang. Okay, and okay, am I good? Yes. And then B prime, we have a formula for that, done. F, we have a formula for that, done. And this is what I call homework assumptions, which are 10 to the 6, 10 to the 3, this equation and this other equation. If everything else is, all this stuff is true, then now we are done with the specimen. We got everything. And now we can proceed to fatigue of components, but I will do in another video because this is taking a lot of time. Okay, so we go like that. Yeah, but before we leave, I'm going to do an example so that then you can do homework. Okay, this will help you definitely with homework. It's a simple example. So calculate the fatigue strength SF of the R.R. Moore specimen. It's a specimen. Okay, and it says what is the fatigue strength at n equal to 2 10 to the 5 fully reversed cycles. Well, this is redundant because if it's R.R. Moore specimen, it has to be fully reversed. All right. Well, I explained that in the previous video. You go plus minus with a sinusoid. All right. Now the data is SUT 170 and 170 is less than 200. Okay, so SE prime from the estimation formula is SUT divided by 2. Remember the 0.5? So 170 divided by 2 gives me 85. So that means that SE prime is 85. Without data, I can assume that that's the number. And also they tell me, okay, assume this and this, which is normal when you don't know anything, then you assume this. And okay, so then definitely immediately what I need next is this sigma F prime, which is SUT plus 50. That's what we estimate, and I take this to 20, all right? Okay, then I use the two formulas that I derive, and B prime is minus log of this time divided by this, like that. And of course, this NE being 10 to the 6, the log is 6, so there's the 6. Minus and log of this ratio, which is sigma F prime is 220 divided by SE prime, which is 85. Yes, is this parenthesis here. Oh, I got worried because I couldn't see this, but no, here it is, the 6. Yes, so this is like this, and it gives me this number, which yeah, is reasonable, minus 0.068883. So you see, I keep 1, 2, 3, 4 significant digits. That is 4 digits that are not zero. I don't care how many zeros there are here. 1, 2, 3, 4, I keep. Okay? So I got B prime. Once I have B prime, I take NT, which is 10 to the 3s. Okay? And the B is negative. So then here comes the negative. This 3 is from N to the T, that is 10 to the 3. Multiply by this number, which is this number. Put it there. And then the 220 is sigma prime. Yes, it's here. And SUT, they told me is 170, and I calculate that, and I get F 0.8. Yes, I'm happy because 0.8 is reasonable. Okay, now a specimen, here I put has no modifying factor. You don't know what modifying factors are, but the modifying factor is what we need to make a component, to calculate a component. So what I should have put here is that a specimen doesn't care about anything, surface, temperature. A specimen is a specimen. Okay, but it's easier, it's faster to say it has no modifying factors. And in the next video, you'll understand what modifying factors are. So then B prime, A, sigma prime, SE prime, because it's a specimen. So everything is the same. And I can use the normal equation, which is valid for a specimen, components, parts, never mind. As long as I put A sigma prime and B equal to B prime, which I calculated right here. And so I put these numbers over here in this equation. The N is 2 10 to the 5 because that's what they asked me, like that. Multiply to the power B, which is minus 0.68 from here. And then multiply here by A. A is equal to sigma F prime, and sigma F prime I calculated right there. And I go there, and it's 94.96 kpsi. Okay, so let's see, is this reasonable? Okay, the SC prime, which is here, it's 85. And the SF that I can use in the design, I draw the arrow like that because I'm going to use this number out. So it's 94, so it's not a lot more than 85. Why is so little? Because you're asking for a lot of cycles, you know, 2 times to the 10 to the 5. So it's very close to 10 to the 6, so you cannot expect too much. And if we compare to SUT, where SUT was given to us is 170. That's a big number. All right, so 170 drops to 85 if you go to infinite life. If you want 2 10 to the 5, 200,000, you can get a little bit more strength, 95, okay, a little bit, you gain a little bit, not much. So everything looks good for this example. And then, okay, to end this, like always, we have the videos, where the videos are for those registering the class, they're there. Homeware, everybody knows where Homeware is, and the app that is not released yet, it's here, okay? Good, okay, so thank you very much, and thank you so much for your patience, all right? So we're done.